Welcome to the class on inverse Laurent transformation. If one remembers the inverse Laplace transformation well, this topic should be rather easy. Using the inverse Laurent transformation, a discrete function in the time domain can be determined, specifically depending on the sample number, based on a discrete function in the domain of a complex variable z. We will use the residual method. The appropriate formula is shown on the slide. The basic difference with respect to the inverse Laplace transformation is the variable z instead of s. Moreover, instead of e to the power of st, we have z to the power of n minus 1 in the formula. At the end, one can see the sum of the Kronecker deltas, but in most tasks there will be only one delta, for k equal to 0. In such a situation, use the formula fp of 0 is equal to the limit of f of z as z approaches 0. More Kronecker deltas will occur only in the specific case, which we will consider in the task. The last difference is that in the inverse Laurent transformation, calculations can normally be performed also in the case in which the degree of numerator is equal to the degree of denominator. And this ends today's theoretical introduction. The remaining two issues, that is, determining the recursive equation and determining the final values of step and impulse responses, will be presented at the end of the recording. Now let's move on to the specific examples of tasks. The content of the task is: determine the original of the function f of z equal to In both cases, we have single poles, so there should be no problems with calculations. However, before we move on to writing the limits, I encourage you to start all calculations with beginning value. It's very easy to forget about it later. In our function f of z, we substitute 0 for each z. And this value is the parameter for the Kronecker delta. Then we move on to the limits for individual poles. This middle element must be always shortened with denominator. In the latter notation, fractions to the power of n minus 1 must be in brackets, because on the one hand the minus is also raised to this power, and on the other hand, if this bracket were not there, only numerator would be raised to the power. The task will contain information that the result should be the sum of the components, without unnecessary brackets, and wherever possible there should be a dependence on n, and not, for example, n minus 1. In our case, both powers should have n in the exponent. This can be done in different ways. I will show two and let everyone choose which one they prefer to use. I multiplied by 1, but in such a way that after combining I will have to the power of n. And now I will use the property of powers that if I have two identical bases, the exponents can be added. And this is the result in its final form. Now our task is to calculate the original of the function d of z we have to calculate the original of the function, that is d of n. And this is exactly how the solution should be marked. If someone marks this as I will treat it as a mistake. This marking will be correct if the task contains a command to calculate the inverse Laurent transform of the function d of z. Again, I encourage you to start with beginning value. If the parameter is equal to 0, it doesn't need to be entered into the result. But such short information that this parameter is equal to 0 is necessary. I should see that you have not forgotten about it. The pole is threefold, so the full formula must be used. The remainder of the division is 8 because each bracket gives us 2, and there are 3 brackets in total. Inside we have the product of 2 functions that depend on z, so we calculate the derivative of the product. And again the derivative of the product. The equation has grown a lot, and it's easy to make a mistake. Let's stop the calculations here and return to the equation before calculating the derivatives, that is, here. Please note that the variable z and z to the power of n-1 can be multiplied. Unfortunately, the task requires you to get rid of all unnecessary brackets, so you have to multiply it. The content of the task is the same as before, and the function is If the content of the task is given with negative powers, it is best to transform it to have positive powers. Let's calculate the poles. So we have a double pole in the value of -1/2. Let me remind you that the parameter at the highest power needs to be rewritten. The degrees of numerator and denominator are equal, but we can calculate it in the normal way. The parameter Cp of 0 is equal to 0. In the next task, let's calculate the inverse Laurent transform of the function if, based on the content of the task, we are to obtain the inverse Laurent transform, the result can be denoted by the function small a of n but it can also be written in this task. We have a pair of conjugate poles. The specific pole values are 1/3 j and -1/3 j. Such a task we calculate similarly to the inverse Laplace transform. That is, we determine the double real part and perform the calculations only for one complex pole. You will probably usually choose the pole with plus. Therefore, I will show here the calculations for the pole with minus. And when I was preparing this task, I forgot about the delta. That's why I recommend starting an expression with it. This minus 2/3 to the power of n is a real number, so one can take it out of the brackets. However, the j value can be written as e to the power of j 90 degrees. If you raise a number with power to some power, these exponents can be multiplied. And from Euler's formula we know that I take the 2 from denominator before the real part. But the result has to be without unnecessary brackets, so let's consider another problem with complex poles. First, we need to calculate the poles. We have a pair of conjugate poles, so again 2 real parts. I take 4 from denominator before the real part. And again, this number raised to the power of n must be presented in the polar coordinate system. In the next task, let's calculate the inverse Laurent transform of the function If any pole is located at the origin of the coordinate system, then this is a special case of the task. First, you need to determine an auxiliary function in which there are no poles equal to 0. Then we calculate the original of the function f1. Please remember about subscript and superscript here. In the next step, the function f1 of n-3 should be obtained. This 3 results from the fact that in the function f of z there was a triple pole at the origin of the coordinate system. We have to substitute n-3 in every place where was n. Our final result is therefore equal to Please note that the triple pole in z equal to 0 is the same as in numerator z to the power of -3, and the latter we used earlier as a delay. And indeed, it is a delay of 3 samples. But what does this do? In control, we assume that for a time less than 0, the function is equal to 0. Therefore, if a function has been delayed by 3 samples, it means that the first 3 samples, counting from 0, must be 0. Therefore, the following 3 conditions must be met. So, for n equal to 0, for n equal to 1, and for n equal to 2, our final function f of n must be equal 0. These 3 deltas are for just that. To determine fp of 0, we take the original of the function f and substitute 0 for the variable n. the Kronecker delta is non-zero only for 0 argument, so this -2 will be zeroed out. And the other two deltas will also zero out, so I don't write them anymore. We know that f of 0 should be equal to 0. Using this equation, we need to determine the parameter fp of 0. We calculate fp of 1 and fp of 2 in exactly the same way. And all that remains is to write the result by substituting individual elements. At the beginning, I mentioned that there would be two more types of tasks included in this topic. The first issue is determining the recursive equation based on discrete transfer function. Let's do the calculations for the discrete time transfer function . This issue should not be difficult, especially after determining the discrete transfer function using finite difference methods. That's why I'm going to write a lot, so that everyone understands what I'm getting from, but when solving it, you can skip most of calculations. Transfer function is the ratio of output to input. We multiply diagonally. Now we will calculate the inverse Laurent transform on both sides. The inverse Laurent transform of capital Y of z is small y of n, and multiplying by z to some power means shifting by the appropriate number of samples. We have the difference equation, but in impractical form. In a recursive equation, I want the y of n to be on one side and the rest of expression on the other side. But this y of n should depend on the values from the previous samples, or on the input in the same sample if the object has equal degrees of numerator and denominator. So, in the arguments, we should have n-1, n-2, and so on. We can get this by shifting the entire equation by 3 time steps. That is, we need to subtract 3 in each argument. We could achieve the same effect if we multiplied the numerator and denominator of the discrete transfer function by z to the power of -3. Now I move everything except y of n to the other side of the equation. But this is an equation for 3 y of n, and I want an equation for just y of n, so we have to divide both sides by 3. And this is the finished recursive equation. Based on it, one can calculate the output of the object in subsequent time steps, knowing the value of the input signal to the object. The last type of task is the calculation of the final values of step and impulse responses. The final value of the step response is denoted by and it is calculated from the formula whereas the final value of the impulse response is The task may or may not contain information about whether the object is stable or whether a given final value exists. If the content of the task shows that the final value exists, just use the given formulas. However, if one don't know whether the object is stable, one should first check where the poles are. I would like to remind you that for the final value to exist, the thing from which we calculate the limit must have all its poles inside the unit circle. Therefore, let's consider a task in which we are to determine the final values of the step and impulse responses for the discrete transfer function First, the location of the transfer function poles must be calculated. But to avoid mistaken, I will change the powers to positive ones. Therefore, the transfer function from the task content can be written as so, one pole of the object is inside the unit circle, and the other is on the unit circle. Hence, the final value of the step response doesn't exist. And the final value of the impulse response will only exist if the pole on the unit circle shortens. The pole on the circle has shortened, so this final value exists. And one more task of the same type, that is, determining the final values of the step and impulse responses for the discrete time transfer function. Here we are no longer able to easily calculate the pole values, but we can use the previously learned stability criteria approaches. All poles are inside the unit circle, so both final values can be calculated. And finally, I would like to show you where the two formulas we used in these tasks come from. In the first class, which included Laurent transformation, the formula for the final value was given, and specifically it was Here we consider only two types of signal, step response and impulse response. Let's write the Laurent transforms of these signals below. In the domain of a complex variable, the output signal is equal to the transfer function times the input signal. So let's write the formula for the final value of output signal. And that's why these formulas look like this. And that's all I wanted to show you today. Thank you for your attention and have a nice day.